Hey. Small wait like one more minute. So maybe just for your benefit, I mentioned this last time, but so this is the textbook that I'm going to be mostly following. It's on the syllabus on Blackboard. You can get a copy of it. It's not expensive. It's about $30. Or what I found is you can also Google the title of it, and there's a version of it online, which may or may not be legal. Houston, Paul Houston. But you can find it on the.
I have it since.
Okay, you can find it on the syllabus. And later in the course, I'll be taking some material from some other books, but then I'll copy the relevant sections. Is there anything else on the syllabus that's important that I'm forgetting? Probably not. Just take a look at it. If you have any questions, let me know. Okay, let's go ahead and get started. So last time, we started talking about reaction dynamics, and we started talking about state-to-state reactions. So, in kinetics, we were talking about overall reaction rates, one species being converted to another. But in reaction dynamics, we're really looking at the microscopic details of how reactions take place. And so you can look at, for example, how the rate depends on the internal state of a molecule, like the rotational state, the vibrational state, and so forth. And we looked at an example, right? Fluorine atoms reacting with H2 molecules, and they make HF in a inverted vibrational distribution. Okay, so how do you measure all these things, right? Because you can measure, state-to-state effects on reaction rates. You can measure angular effects, orientation effects, and so forth. And so that's what we're going to start talking about today is molecular beam experiments. So a molecular beam is basically exactly what it sounds like. It's a beam of molecules that propagates in a particular direction. And how do you generate a molecular beam? Well, typically you have a nozzle where you have a reservoir of gas at high pressure. And the nozzle basically emits molecules into a vacuum chamber. And then located a certain distance away from the nozzle, you can have either an aperture or a skimmer. So a skimmer is just sort of it's like a little metal part that's about this big. It's cone shaped, and it's got the tip of the cone cut off so that there's a little aperture. And so that's what I'm sort of representing here is a skimmer mounted on a chamber wall. And you have a couple of these. And basically the effect is that only molecules that are coming along a particular direction are allowed to pass through the skimmer so that you get a directed beam of molecules. Okay, so this is a nozzle. This is being pumped, right? So there's a pump here, there's a pump here. This is a skimmer. And this region here is the molecular expansion. And there's two regimes that you can have. So in the previous, at the beginning of our kinetics course, I gave you a homework problem involving an effusive molecular beam. that's where you have a relatively large aperture. The aperture is large relative to the mean free path of the molecules so that they emerge from the nozzle at a well-defined temperature. But if you make a very small aperture in your nozzle, then you get what's called a free jet expansion. That involves many molecular collisions. And these collisions basically convert all of the energy that's stored in the internal degrees of freedom into kinetic energy. And it makes the gas very cold in terms of its internal degrees of freedom. But it makes it propagate with more kinetic energy. So in a free jet expansion, and this is called these conditions are called supersonic because when you convert the internal degrees of freedom into kinetic energy, you end up with molecules that are traveling faster than their original speed of sound. So in a free jet expansion, energy in internal degrees of freedom is converted to kinetic energy. Okay? And so there are several consequences of this. You get a, like I already said, you get a low internal temperature. That means if you describe, for example, the vibrational distribution or the rotational distribution of the molecules by a Boltzmann distribution of states, you get a very, very low effective Boltzmann temperature of typically 5 or 10 Kelvin. So low internal temperature, so everything is in the lowest few states. You end up with a high kinetic energy. And you also, after the free jet expansion, you end up with conditions under which there are no molecular collisions. And you also get a very narrow velocity distribution. And the way that you can think about that as an analogy, let's say there's a whole bunch of like bumper cars on a highway, right? Like Mario Kart. And they're all, very densely packed close together. They're all going different speeds. Then in this region where you have a lot of collisions, the ones that are going too slow, they get bumped into by the ones that are behind them. The ones that are going too fast, they bump into the guy in front of them. And after, a number of collisions, finally, you end up in a state where they're all going the same speed, right? If you're going too fast, you're going to bump into the guy in front of you. If you're going too slow, you're going to get a bump that'll accelerate you. Okay, and this cooling of the internal degrees of freedom that leads to a fast velocity. Basically, the enthalpy that's stored in the gas at room temperature gets converted to kinetic energy, so that the most probable velocity in a supersonic jet expansion ends up being given by root 2 times the heat capacity at constant pressure times temperature over the mass of the molecule. This is for pure gas. In a supersonic expansion. Okay?
Sorry, what is M in the equation?
The mass of the molecule.
Okay, the mass of the one molecule.
Yeah, basically 1/2 mv squared equals C times T. So the kinetic energy, mean kinetic energy equals, yeah, CT. Okay, so for example, if you have a rare gas, you end up getting most probable velocity equals root 5 kT over m. So for helium, if you have helium at room temperature in your reservoir, then you end up with a molecular beam that has a speed of approximately 1800 meters per second. Or the units that I prefer in the lab are 1.8 millimeters per microsecond, right? Because that's more on the length scales and time scales that you're working with in the lab. Okay, and you can also seed. You can do what's called seeding. So it's possible to seed a heavy molecule into a light carrier gas. To obtain high kinetic energies. Right, so if you have a bunch of, Mario Karts, but then, there's a few 18-wheelers in the Mario Karts, if they get enough collisions from the little, small, fast molecules, then they'll basically be carried along at the same speed. And then you have a Mack truck that's going really fast, so it has a lot of kinetic energy, and it can overcome pretty high reaction barriers, right? So if you want to study a reaction that has to overcome a high barrier, this is one good way to do it. Okay, and so just as an example, if you look at the velocity distribution in a molecular beam, so here's the distribution of velocities versus speed in meters per second, then, right, so this would be seconds per meter. A Maxwell-Boltzmann distribution, if we're talking about like helium, that would be centered around somewhere like maybe 1200 meters per second. But if you put it into a supersonic beam, if you make a supersonic beam of helium, then you get a very narrow distribution at around 1800 meters per second. So this one's a supersonic beam. And this one is a Maxwell-Boltzmann distribution. At 300 Kelvin. Okay, so we've been talking about rate constants as a function of the kinetic energy. Well, here's how you get a very specific kinetic energy: is you create a molecular beam, and you can tune the energy by changing the gases in the molecular beam. Right? If you put more heavy, a heavier seed gas like argon, then you'll get a slower speed. If you put a light seed gas like helium, you're going to get a faster speed. Okay.
Professor,
Yeah.
why is the supersonic beam speed is not, the maximum of the Maxwell-Boltzmann there? Is there some...
Why is what?
I'm not sure if I understood correctly, but why is it not in the maximum of the maximum?
The reason is because the no, it's a bit faster. Yeah, I guess in the case of helium, you don't have internal degrees of freedom, that you're putting more energy into the, yeah, actually that's a good question. I guess it must have something to do with the fact that the isotropic gas has a speed distribution in all directions, and some of that speed gets directed in the direction of the expansion due to collisions that are happening right at the orifice.
You mean the reason is that the geometric thing?
I think so, but actually that's a good question, I'm not sure. So if you have a molecule, like polyatomic molecule, then the reason why in the supersonic beam it's faster than the average of the Maxwell-Boltzmann, or the most probable Maxwell-Boltzmann speed, is partially due to the fact that the internal degrees of freedom, right, the energy in internal degrees of freedom is being converted to kinetic energy.
Okay.
In helium you don't have that, but I would have to check, you know, is this energy the same as the average kinetic energy? It's definitely faster than the most probable. It might be similar to the average kinetic energy of the Maxwell-Boltzmann. But I don't know that off the top of my head.
Okay.
Okay, so then if you want to study, let's say you want to study a bimolecular reaction, right? And you want to know all these details. What's the influence of, you know, vibration, rotation, angle of collision, orientation, etc. Then you can do a crossed beam experiment. Okay, and basically the way that looks, instead of one molecular beam, you have two molecular beams. Right, so there's a couple skimmers here. Then you have a different molecular beam. And you can change the orientation, but for simplicity, let's just assume they're at right angles. Right, so basically you have two molecular beams. In this case, they cross each other at 90 degrees. And then the molecules in the two molecular beams can scatter off of one another, either, you know, elastically, inelastically, or they can do a reaction and scatter. And then you have some sort of detector. And in the sort of traditional molecular beam experiments, this would be some sort of quadrupole mass spec that is mounted on a large translation stage so that you can rotate it and measure the scattering products at different angles. But in more modern approaches, usually what you would do is you would use ion imaging, where basically you come in with a laser and you ionize the scattering products, and then you image them on a detector that lets you figure out the angles and the velocities of the scattering products. Okay? All right, so, you know, what do we really want to know then about this reaction? Well, it's a little bit complicated because in the lab frame, you're seeing something that's a little bit different than what you would be seeing if you were observing the reaction in the center of mass frame for the collision. So in the center of mass frame, you know, if you have let's say you have a reactive collision, right? You want to study some chemical reaction. Let's say you have a molecule, A molecule, and it's reacting with a CB molecule, right? Then, you know, maybe the A molecule is coming in like this, the CB molecule is coming in like this. They undergo a collision. The way I have it drawn here, the impact factor is greater than 0, right? And maybe B gets transferred to A, so then you have a BA scattering this way, and you have a C scattering this way. Right? So this is kind of the information that we want, is we want sort of to learn, you know, how this reaction happens in the center of mass frame. Okay? And we talked in the beginning of the kinetics course already a little bit about center of mass frame versus the so like the relative velocity versus the center of mass velocity, and you know that the total kinetic energy can be written as the sum of the kinetic energy in the relative velocity frame, right, times the reduced mass plus the kinetic energy in the center of mass frame. Oh, sorry, this needs a square. Right, and the center of mass velocity gets multiplied by the total mass, right? M is the mass of the two colliding partners. Okay, and this center of mass velocity, by definition, it's defined as, it's basically the weighted average of the velocity of the two particles that are colliding. So it's mass of particle 1 times the velocity vector of particle 1 plus mass of particle 2 times the velocity vector of particle 2 divided by the total mass. Okay? And so as a consequence of this definition, right, this quantity in the denominator here, this is the total mass m. So m times the center of mass velocity vector is equal to m1 v1 plus m2 v2, which this is simply equal to what? What is this quantity? MV. Yeah, momentum. This is the total momentum of the system. If your system is particle 1 plus particle 2, then this is the momentum. And momentum, as long as there's no external forces, is a conserved quantity. And so as a result, the center of mass velocity is conserved during the collision or the reaction. And so only the relative velocity is available in order to provide energy for the reaction. The center of mass component of the velocity has to be conserved. Okay? All right, so our next task, what we want to do is we want to compare, we want to figure out what's the relationship between the lab frame, right, for describing these velocity vectors versus the molecule frame, right, in the center of mass frame, right? So basically, you know, if you're observing the reaction and you're somehow traveling along the center of mass vector, you want to be able to observe this reaction happening like this. Okay, so let's say you have in the lab frame you know, you're doing this experiment, right? So in the lab frame, you could draw two vectors, right? Here's the velocity vector for collision partner 1, and here's the velocity vector for collision partner 2. Right, so here's the origin, right? This point corresponds to 0 velocity in the lab frame. And then we want to relate, you know, we want to describe these two velocities in the center of mass frame. So let's start with V2. And if you take the V2 vector and subtract off the center of mass velocity vector, then what do you get? Well, in order to write this in a form that is meaningful, we're going to do a little trick. We're going to take V2 and multiply it by 1, right? So we're going to multiply it by M1 plus M2 over the total mass, right? So this quantity is just 1 times V2 minus V center of mass. Okay, and so that lets us break up V2 into 2 different parts. So we have M1 over M V2 plus M2 over M V2 minus V center of mass. Okay, and then from our definition over here, right, V center of mass equals M1 V1 over capital M plus M2 V2 over capital M. We can solve that for M2 over M times V2. And this term here, just solving this equation for the second term here, right, M2 V2 over capital M, that's equal to V center of mass minus M1 V1 over M. And so if you plug this into this expression for here, then you're going to get, the V center of mass is going to cancel, and you're going to get M1 over M times V2 minus M1 over V1 over M. Okay, and so that brings us to the other definition that we need, right? So we defined V center of mass. The other velocity that we need is the relative velocity. And the definition of relative velocity, well, in this case we could just define it as V2 minus V1. Right, so the relative velocity in this picture would look like this, right? Here's the V relative. Okay? And so this expression here is simply equal to M1 over capital M times the relative velocity. Okay, and we can do a similar derivation. I'm not going to go through the whole thing because it's exactly the same. We can also solve for V1 minus V center of mass. And that's going to equal to minus M2 over M times the relative velocity. Okay, so what does that mean? Right, that means basically that if we draw a center of mass vector, then V2 minus that center of mass vector, well, it's proportional to VR. And this other one is also proportional to VR. And so therefore, it must be that if you draw on this diagram V center of mass, it has to somehow intersect this VR vector in such a way that, after subtracting off V center of mass, the relative velocity of particle 2, which we'll call U2, that's going to equal M1 over M times VR. And the component of relative velocity that's attributable to particle 1, that's just minus M2 over M times VR. Okay, so if you were riding along, let's say you're sitting on top of a helium atom in a molecular beam that's going along the center of mass direction, then basically you would look to your left, and you would see particle 1 coming straight at you, and you'd look the other way, you'd see particle 2 coming straight at you, and they'd both be directed along this relative velocity vector, right? And in the center of mass frame, they're just going to come together, collide, come apart, right? But the impact parameter is not necessarily 0, so you could also have glancing collisions, right, leading to some other angle of the products, right? But they're just going to come like this, right? But in the lab frame, of course, they're actually coming like this. But subtracting the center of mass frame, you get these components that are proportional to relative velocity. Okay, and which marker was I using? Okay, that one's good enough. So in the center of mass frame, the velocities are along the relative velocity direction. And you can obtain the relative magnitudes from the masses. And in fact, if you look at the momentum in the center of mass frame, right, m1 times mu, or u1, right, this is the center of mass component of velocity, equals minus m2 times u2, right? So in this center of mass frame, the momenta are equal and opposite. So the momentum in the center of mass frame is 0. And it's easy to see that, right? Because if you take, if you take u1 and multiply it by m1, then you're going to get minus m1, m2 over m times vr. And this one, you're going to get m1 times m2 over m times vr. And you can see that these quantities are equal and opposite. Okay, and so also, if, let's say that particle 1 is really, really light, particle 2 is really heavy, then which one is going to be going faster in the center of mass frame? If particle 1 is really light, particle 2 is really heavy, which one's fast?
Light.
Yeah, the light one is going to be faster, right, because it's m2 over m, right? So if m2 is heavy, the light one has to go faster, and that also makes sense because we've said that the momenta have to cancel. So if you're really light, then you have to have a high velocity in order to cancel the momentum of a really heavy object. Okay? Okay, so we've now sort of described the situation before the collision, right, in two different reference frames, lab frame, center of mass frame. So what about after the collision? What are the velocities after the collision? Okay, so in general, we don't know all the details. We can't a priori know all the details about the velocity vector, but we can know a lot just by applying conservation of momentum and conservation of energy rules. So based on conservation of momentum, right, if there's no change in the center of mass momentum, and the relative center of mass frame momentum is 0 before the collision, then the center of mass momentum after the collision also has to be 0. Right? So if, and in general, there could be a reaction going on during the collision. So in general, the masses of the two particles could be changing, right? You could be transferring an atom from one molecule to the other, for example. So after the collision, if you have a mass m3 and a center of mass frame velocity u3, then m3 u3 plus the mass of the other particle m4 u4, right, times its center of mass velocity, this has to be 0. Right, this is conservation of momentum. And we also can take advantage of conservation of energy. So if we write the total energy in the center of mass frame, right, the energy in the or the energy of the center of mass component is conserved, of course, but what's the energy in the center of mass frame? Well, that's just 1/2 m3 times u3 squared plus 1/2 m4 times u4 squared. Okay, so what's that going to be equal to? Well, we came in with a certain energy, right? We can compute, what's the part of the energy that's along the relative velocity direction, right? So that's the incoming relative kinetic energy. But is the final energy necessarily equal to this energy? Where else could energy come from? Yeah, exactly. What if you have a vibrationally excited molecule colliding with some other molecule in an initially excited state, and then they collide, they interact in such a way that they end up making products that are in the vibrational ground state, right? Then you could have an extra release of kinetic energy due to the de-excitation of the internal modes, right? Or what about the picture that I drew, where you had A reacting with CB to make BA plus C? Is there another, form of energy there? What about the energy that's stored in the CB bond? What's happening to that energy? I mean, there's energy in the bonds, and so if you do a reaction, right, the reaction's either exothermic or endothermic, and that energy has to come from somewhere, right? So we need to add a second term here. I'll call it EX, where X stands for exoergodicity. And this depends on the initial and final states. Okay, so this is the exoergodicity of the I to F process, right? The process that takes initial molecules in state I to final molecules in state F. Right, and as we have already said, this energy could involve changes in internal quantum numbers of the molecules. It could involve the energy due to a chemical reaction, and so forth. Okay? And so this is going to be equal to 1/2 times the reduced mass after scattering. I'll call that mu prime, right? Which is not necessarily equal to the reduced mass before scattering, because you could have, M3 and M4, they add to the same mass, but they're not necessarily equal to M1 and M2, right? And then this has to be multiplied by the relative velocity after scattering squared. Okay, and this is not necessarily the same as the relative velocity before scattering. Okay? So we could draw vectors for V3 and V4, just like we did with V1 and V2 over here, right? And if we then ask ourselves, okay, what are the center of mass components of V3 and V4? Right, so, well, first of all, VR prime, right, which we defined over here, that's, we'll define that as V4 minus V3. And if we analyze this in the same way that we did over here, then we can determine U3 and U4, and we're going to get an analogous result. U3 is equal to minus m4 over m times the relative velocity, and U4 is equal to m3 over m times the relative velocity, where m is the total mass, right? It's equal to m1 plus m2, and it's also equal to m3 plus m4, because mass is conserved. Okay, so what if we drew a diagram for this? So initially we had a U1 and a U2, right? And it looked kind of like this. So we have U1 like that, and we have U2 like this. And let's say they undergo a collision, maybe there's a transfer of mass, and then maybe we end up with some U3 and U4. And so you know that, by conservation of momentum, U3 and U4, the momenta contributions have to cancel each other, so they have to be in opposite directions. So maybe here's U3 and here's U4. And so you can get the magnitudes of these vectors from conservation of energy, and the relative direction has to satisfy conservation of momentum. But in general, there could be any angle, right? So you could have some theta angle, right? And we don't know that angle. Okay? But we can make what's called a Newton diagram to explain where you'll find the particle in the lab frame. Oops. Okay, so let's say we had some, this was the zero of velocity in the lab frame. We had some velocity of particle 1 and 2. This gave us velocities in the center of mass frame, U1, right, U2, right? The center of mass velocity was like this. And then let's say you had a scattering process, and it gave you, like we said over here, some U4, and it's going like this. Okay, so in general, if you look at a whole bunch of these scatterings, right, a whole, two molecular beams scattering from each other, there could be a distribution of these angles, and you could observe particle 4, right, so this is U4, you could observe particle 4 anywhere on a sphere, or a circle, in this planar diagram, with radius given by the magnitude U4. Right, so if you have and so here's the center of mass frame scattering angle theta, but our detector is in the lab frame, and so it's detecting the velocity vector relative to the origin in the lab frame, right? So if you have a particle that's scattering with this velocity, then in the lab frame, oops, well, I didn't draw that very well, but in the lab frame, I'll just change this a little bit so that it matches. So here's U4. This one was U2. You're going to get some capital theta, like this, right? So here's your detector. And in order to, in order to measure all the possible scattering angles of U4, you'd have to rotate your detector around a complete 360-degree circle, basically. Okay, but what about the other collision partner? The way I've drawn it, the other collision partner has a low velocity, right? Maybe it's a heavy species. So if I draw U1, right, U2, and then U3 was maybe coming this way, then, and here's the origin, right? Then it's what's called the Newton sphere for this guy. In the lab frame, if the center of mass velocity is less than if the relative velocity is less than the center of mass velocity, then it's only going to be located over a narrow range of lab frame angles, because you would only have to scan your detector range from this theta 1 to this theta 2 in order to detect all of the possible velocities of particle 3. Okay, does that make sense? Because its final velocity is less than the original center of mass velocity, right? So you can cancel some of that initial velocity from the collision, but not all of it. Okay? Okay, so if you measure all of these angles, right, then you get what's called the differential cross-section for scattering. And the differential cross-section, it's written d3 sigma of, it's a function of relative velocity and incidence angle per unit solid angle per unit final relative velocity. Right, so omega is the solid angle, and Vr prime is the final scattering relative velocity. Okay, and as long as you have random incidence orientations of the two molecules, then the scattering will be cylindrically symmetric about the initial relative velocity vector. Right, and so to see why that would be the case, let's just say you have one particle that's really massive, right? So it's basically standing still in the center of mass frame. You have another particle that's light, so it's scattering off of that particle, right? Well, let's say you have a certain impact parameter, B, right? Then maybe, if you assume random orientations, then basically the scattering process, if you scatter many molecules, you're going to average over all the possible incidence orientations. So you're going to scatter to some angle, right? But if you had minus B, right, B in some other direction, since you're averaging over all the orientations, you would expect the same distribution of scattering, from a different
Angle.
yeah, I mean, same B, but different direction, right? And so basically, that gives you something that's symmetric with respect to the azimuthal angle phi. But there's a certain, right, so like this angle here, right, that's theta, right? And there's going to be a certain distribution of theta. That's what we're measuring, right? When we measure, actually big theta, we measure the lab frame component theta, and then we convert that into the center of mass component little theta. Okay? But because of this symmetry, so when we integrate the differential cross-section, we should get the total cross-section. And we don't have to integrate over the azimuthal angle because it's radially symmetric, so that integral just gives us 2 pi, right? Integrating over phi. But if we integrate over theta, and over all of the possible final relative velocities of the differential cross-section, then it's normalized in such a way that when you do this integral, sine theta, d theta, d r prime, then you get the total cross-section at this particular relative kinetic energy. Okay, that is all that we have time for today. Questions? Sorry?
Definitely, but not this.
These Newton spheres, this is like, if you go to a conference where people are giving talks about molecular beams, like nobody understands it.
Yeah.
Because it's a slightly confusing topic. So people will show diagrams of their Newton spheres, and then people are kind of like, oh, okay.
Unfortunately, I have to work with these things for the rest of my
Well, surface scattering is a little bit easier.
Because I am guarding.
Because the surface has a fixed orientation in the lab frame.